Every second of our lives, we're basically swimming in an invisible ocean of waves. We just call it sound. But what is it, really? It's not just something we hear. It's an actual physical journey. A story that starts with a tiny little vibration and, believe it or not, ends inside our own minds. And in Missexplainer, we're going to follow that journey from the very beginning to the very end.
I mean, really think about that for a second. What would a whisper actually look like? Maybe a tiny, delicate ripple in the air. And a clap of thunder? Probably a huge, chaotic explosion of energy, right? Trying to see sound is really the key to understanding it. And that's exactly what we're going to do.
So this is the big idea we're going to unpack. From the quietest little hum to the loudest roar you can imagine, every single sound is literally a wave of energy that's traveling through the world with one goal: to reach you. So let's trace its path, from the instant it's born to the moment it's gone.
So where does it all begin? Well, every sound, no matter what, has to start at a source. Let's just picture a single guitar string. It's sitting there, silent, perfectly still. But the moment you pluck it, bam, the journey begins.
And that's what a sound source is. It's anything that moves and creates a vibration. It could be your own vocal cords when you talk, a speaker cone bumping back and forth, or, our guitar string. The main rule is, for sound to even exist, something has to move first.
And that movement? It has a technical name: oscillation. But really, it's just a fancy word for a repeated back-and-forth wiggle. And this simple little oscillation, this wiggle, is the spark that ignites the sound wave, sending these ripples of energy out into the air.
Okay, so once that wave leaves its source, it has its own unique characteristics, an anatomy that we can actually measure and describe. This is how we can tell the difference between, say, a low bass note and a high-pitched whistle, or a quiet sound and a really loud one.
So, let's start with frequency. This is all about the speed of that initial wiggle. How fast is the source vibrating? A slow, kind of lazy vibration creates a low frequency, and our brains hear that as a low pitch. But a really, really fast vibration, well, that creates a high frequency, and you guessed it, a high pitch.
And we actually measure this speed in something called hertz, or just hertz for short. So when you see a measurement like 440 hertz, it literally means that the sound source is vibrating back and forth 440 times every single second.
Okay, so if frequency is about speed, the next part of the puzzle is amplitude. And amplitude is all about power. It's basically the size or the strength of the wave. A small, gentle little vibration has a low amplitude, and we hear that as a quiet sound. But a big, powerful vibration, that creates a high amplitude, which our brain processes as loudness.
We measure that intensity in decibels, or dB. That's the unit we use to describe everything from a whisper in a library to a jet engine taking off. So, to sum it up, frequency gives us pitch, and amplitude gives us volume. So we've got speed and we've got power. The last piece is the physical size of the wave itself. Wavelength is just the distance the wave covers before it repeats, so the space from the very top of one wave to the top of the next one. It's the literal size of that sound as it travels through space. But sound is so much more than just pitch and volume. I mean, why does a flute sound so completely different from a drum, even when they're playing the exact same note at the same loudness? Well, it all comes down to the character of the sound wave itself. And that character really boils down to a battle between order and chaos. A tone, like a single clear note from a piano, has a clean, predictable, repeating wave pattern. It's orderly. But noise? Noise is just pure chaos. It's a total jumble of irregular, disruptive waves with no clear pattern at all.
And then there's this amazing thing called resonance. Think about pushing someone on a swing. If you push at just the right moment, matching its natural rhythm, right, they go higher and higher. It's exactly the same with sound. The vibration of that single guitar string is actually pretty small, but the wooden body of the guitar is built to resonate with it, to vibrate along with it, which amplifies the sound and gives it that rich, full character we hear.
So our sound wave has been born, it's got its unique character, and now it's traveling out into the world. But the world isn't an empty vacuum, right? The wave starts interacting with the environment all around it, and that changes how and even when we hear it.
You see, sound waves don't just travel in a straight line and then, poof, disappear. They bounce. An echo is really just a sound wave hitting a hard surface, like a canyon wall or a big building, and reflecting right back to your ears. It's literally the sound taking a round trip. Okay, But what about some of the really weird things sound does? Here's a classic you've definitely heard. An ambulance is racing towards you, and its siren sounds really high-pitched, right? The second it passes you and starts moving away, the pitch suddenly drops. Nee-yo! But why? The siren itself isn't changing. While this is the super cool Doppler effect, as that siren is moving towards you, it's kind of catching up to its own sound waves, squishing them together. That means more waves are hitting your ear per second, which is a higher frequency and so a higher pitch. Then, as it moves away from you, it's stretching those waves out behind it. Now, fewer waves hit your ear per second, so you hear a lower frequency, a lower pitch. It's the same sound, but its motion completely changes how we perceive it. So, we've followed the journey of all this sound that we can hear. But here's what's truly amazing. The vast, vast majority of sound in the universe exists completely outside the range of our perception. See, our ears can typically only pick up frequencies somewhere between 20 and 20,000 hertz. Anything below that is called infrasound. Think of the deep rumbles from elephants or volcanoes that we feel more than hear. And anything above that is ultrasound, like the super high-pitched calls that bats and dolphins use. And of course, we've figured out how to harness this invisible world of sound. An echo sounder, which you'll find on ships and submarines, sends out these quick pulses of ultrasound. Then, by measuring how long it takes for the echo to bounce back from the seafloor, it can map the ocean depths with incredible precision. Pretty cool, right?
And all of this brings us to a really fascinating puzzle. We said that sound has to start with a vibrating source, but what about tinnitus? This is when someone perceives a sound, like a ringing or a buzzing, when there is no external sound source at all. It kind of challenges our entire definition of sound's journey, doesn't it?
You know, we followed the physical journey of a wave, all the way from a vibration to an echo. But something like tinnitus shows us that the final destination, the actual experience of hearing, happens inside our own heads, which leaves us with one last question to think about. If a tree falls in a forest and no one is around to hear it, does it make a sound wave? Well, yeah, absolutely. The physics are there. But does it make a sound? I guess that all depends on where you believe sound truly exists.